Hello and welcome everybody. Say hello in the chat. Can you hear me well? And we can start very soon with our topic RDFs and graphs for today, especially RDFs and SPARQL. Okay. Does it still say live in 24 hours? I think there was a mistake. I saw it also, this message, but yeah. Does it work now? Because I think I can change it. Cool. No, error saving. I cannot change the date, the publication date of this video, but I think it works, right? Can you hear me? Okay. I choose the 2nd of June as a live date and not the 1st of June. Today is the 1st of June. Okay, we will talk about RDF. Last time in the last video I already introduced RDF, and today we will see how we can query RDF data. RDF is used in the semantic web. Semantic web is first of all a metadata collection to standardize metadata, to say each person has a birth date and a birthplace and a name and so on, and not a date of birth and so on. So when many people make databases, they differ. They have different kinds of heterogeneity. So there are so many forms of heterogeneity, structural heterogeneity. You can do things in this data model, that's data model heterogeneity. You can use arrays, or you can create tables for storing the same thing of data. You can use different encodings, you can use different namings, different languages for column names, and so on. So we are very free when we use a database, and that's true for all databases. We can name our columns as we want, and first of all we need a standard so that we unify things. And these standards in the semantic webs are also called ontologies. This is metadata to describe concepts and the relationship between those concepts. So for example, here's the concept of a game. Game is not a thing of itself. It is a sub thing of creative work, and a creative work is a sub thing of a thing, and so on. And so we standardize these entities here, these entity types, and yeah, basically someone else can use a different standard. This one is the standard used by schema.org. So schema.org standardizes a lot of, not a lot of things, but some of the things. Let's take a look. Schemas, full list of types. So they have people. So a thing has a subtype person, and as we saw, a thing had a name here, text, name of the thing. So everything has a name, but a person also has a here, the given name. They call it given name, not first name, given name. So it is standardized by schema.org. And we will take a look at other schemas, because this is not describing everything. When you want to describe a city, there's a place, a person, a game, that's under creative work. but of course there are limits. Let's say music albums or songs or bands. This is not part of this schema, then you have to use another schema. Within the semantic web, you can use RDF to describe some facts, but you can also embed the facts which are understandable by a machine within a web page. A web page is typically made for humans, so this web page can be understood by a human. The human reads the page and then gets some knowledge. And to increase the knowledge of a machine, we can enrich this website by semantic information using annotations here. This heading is not just an arbitrary heading, but it is a heading that defines the name of this thing here. So the whole div, which closes here, describes a thing of type game. So everything part of this div describes the game. Here's the name of the game, here's the publisher, and so on. So the name is a text, a string, and the publisher is a reference to another entity, the publisher Hasbro, which is described here. And with that, we can describe a whole big graph of knowledge. The graph from before looks like this. We had this last time, and I asked how many resources are in this graph. And yeah, there are more resources than you think. So this 1957 is not a resource. It's a number. It's a literal atomic value. Risk game is also a string. So this is a string, this is an integer, and this is a resource. This is a resource, 2, 3, 4, 5 resources we have here. One person answered, unfortunately incorrect. We have 5 resources here. A resource has a URL, but then you say, oh, what's this URL? Schema : publisher, Jago : Hasbro. So this colon syntax is a short form of a URL because the URL is very ugly and very long, so we use prefixes. We come to prefixes on the next slide. On this slide, I use the full URL for everything. So the URL of this resource, jagoKnowledge.org, resource risk game, has the type, and type is not just type, but a type is a predicate resource. So the predicate is also a resource. The subject, the predicate, and the object are resources, but the objects can also be literal values. So here all our objects are resources, but when we would list the fact risk game is date published 1957, then we would have 1957 here as a literal value. So, and we use different schemas here. One schema of w3.org, they define very, very generic things about RDF. So this is typically also used as the RDF colon prefix. This is the schema colon prefix. So they define what we saw: organizations, people, places, creative work, and so on. I said schema.org does not define music. Of course it defines music and albums. It is creative work. So it is part of the schema.org schema. If you have any questions, simply ask them in the chat. Currently there are no questions. Okay, so RDF basically is a standard to define facts. These facts consist of subject, predicate, object, and the subject, the predicate, and the object can be resources, but the object can also be a literal value. Typically, you have for each thing, like here the game Risk, the predicate type to say that it is a game. Otherwise, it is not clear what Risk is. So when you would think of a graph database like Neo4j, then the type would be the label of a node to describe the label. But here everything is a triplet of subject, predicate, object. And here the predicate is type. Risk game has the type game. Risk game has the publisher, then the URL of the publisher Hasbro, and Risk game has the date published. Ah, okay, I have it here. I was confused with this suffix here. This suffix just gives the further information that 1957 is not an arbitrary integer, but it appends the meaning of the integer. It is a year. So these annotations here for data types can be used to have domains or units. Is it in meters? Is it in centimeters? Is it a year? Is it a price in euro or what else? It adds a knowledge about the number itself. So this is in a relational database, you would store it in an integer column, but you would also store amounts of products in an integer column. So here we can add the information that it means that it is a year. So it is better understandable for the machine. Now is the list of prefixes which I used, and I added some more which I did not use. The prefix RDF stands for this URL, http w3.org, blah blah blah, this version of the schema, and then the Rdf syntax. So we can take a look here, but yeah, we see some definitions. It's not a lot. Direction, language. Where's the type here? No. RDF type. RDF type. This here, this looks very weird. Stands for RDF :type. So the type of type is property and a property is type of a class. So we come to the later. So this is a definition about very generic predicates which we always use. RDFS is, so here you see that the predicate comment come from this ontology RDFS. Publisher, date published are predicates from the schema.org ontology. Then we have things which were already there in XML schema. So for example, dates or things like this year annotation, and data types, string, integer, and so on. This is used from XSD. And Yago, so everything up to here is just metadata. Okay, there are games, and game is a thing, and each game has a name. Each thing has a name, and each publisher has a date of something, and blah blah blah. So this is just describing the data. It's just metadata. But Yago is now a knowledge base which has data for you. So they collect data. They have powerful machines, and they crawl the whole internet, on whole Wikipedia, to find information. And this information is collected and they generate RDF triplets. You can download Yago. It is a very big file. And in each line of that file you have one triplet. For example, Risk the game is of the type game. And when something exists already in the RDF schema or in the schema.org schema, they use this. They don't invent the wheel from scratch. They reuse predicates if they are already there in a prominent other ontology. But sometimes they introduce predicates which were not there in schema.org or RDF, and then they start with Yago : these are predicates from Yago itself. So the idea of knowledge bases is to have linked open data. Let's start with open data. Data is 001111. It's just data you can find in the internet, you can store on a CD, on a USB stick, and so on. Data is data. Open data means this data is accessible for everyone. Everybody can download Corona information, Corona CSV. Coronavirus, our world in data. This is a source of open data, blah, 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 description, and GitHub repository. And here you find coviddata.csv, updated 2 hours ago. And when you open this file, this is very large. It shows, okay, in Asia, Afghanistan, on the, oops, okay, this too, So in each row of this CSV file, you see an information. In this country, on this date, there were so many corona cases and so many deaths and so many vaccinations and so many people lived there in total on that day. And then you can download this data, you can visualize it, make a big graph, or find something out of this data, some insights and so on. So this data is publicly available, and that's what we call open data. So it is not closed data. There's so much closed data in the world, like the products table of Amazon. You cannot download that, but there's also a lot of open data. And linked open data is not like this Corona. This Corona CSV was one file. Linked open data means things are linked to other things. So you have a data set that has persons and a data set that has cities, and then they are linked. In which city does this person live? In which city has the person born, and so on. And this person has 3 children, other people, and so on. So the data is linked together. And when you download linked open data, for example from Yago, then you download it as a large set of RDF triples. So linked open data is structured data that is freely available, that's the open point, and interlinked with other data. And Yago, when you download it, is one knowledge base. Yago stands for yet another great ontology. But basically it's not just an ontology to describe metadata, but it also has many data facts. The data is automatically generated from Wikipedia articles and many other sources. So they have bots. These bots go to a Wikipedia page, for example, n.wikipedia.org. Let's say Regensburg, the city. And a lot of Wikipedia pages have info boxes. They are kind of standardized. So this info box here describes that Regensburg has these coordinates and is in Germany and in Bavaria. So this is very nice. It is well for humans to read and to understand and to compare with other info boxes. So when you go to London, then you have also an info box here, and they are also kind of standardized. So here's also country and region, and here's country and state, but maybe this means this is because it's a different it's differently called in England or United Kingdom than in Germany, how you call the sub states and so on. But let's say population. Here's also population, total and density with bullet points, total and density with bullet points. So it's kind of standardized. It's still flexible. You can add more attributes here, but when you use population, you call it population and so on. And this makes it easy for bots like Yago to extract all this data. When you go to the source of an article, then you see here info box settlement. Settlement is one kind of class that a Wikipedia article can have, and the info box then shows things for settlements. And when you go to people, let's say who should I look at? One, let's say Julia Roberts, actor. Then here's an info box, and then this info box has info box person. So this is made by humans, but it is kind of standardized, and it makes it easy for bots like Yago to extract data. But Yago also extracts data from the Wikipedia free text. This is much more complicated, but otherwise, if they would not do this, they would not have so much information. Not only Wikipedia is a source, but also other sources are scanned by Yago to get all the data they have. And they have 64 million entities. For example, the game Risk, and many people and many cities and so on. So 64 million things. And 2 billion RDF triples which describe those things further and which make connections between those things. And they have evaluated using user studies and so on how accurate the data in Yago is, and they found out that there is an accuracy of 95%. There are other knowledge bases which are also freely available, also linked open data. They also use RDF. DBpedia is a very, very big one. They also have millions or billions of entities for people, places, music albums, movies, games, and so on. And the nice thing is that they are interconnected with each other. So you do not need to decide for one data source. So you can take a look at Yago and you find out, Julia Roberts was born on this date and so on. Let's go to the Yago entry. This is no results. So okay, dancer, British television host, nationality United Kingdom, 1956, QVC presenter. I think this is a different one as the actor. Yeah, it just finds an arbitrary one. We can so this search engine finds displays only the first result, and this is not the actor Julia Roberts, but maybe we can look at this person also called Julia Roberts. We see that they have a birth date, and we use schema.org for these properties, RDF for very general things. These schema.org things are for the person attributes and so on. And here you see OWL, don't know what OWL stands for, w3.org, OWL, same as. So this predicate same as means the thing which we are currently looking at is the same thing as on DBpedia, this resource here. And when I click on this, under maintenance, okay. Very good that I chose Yago for my examples, but both Yago and DBpedia are from Germany. So this is invented by University of Saarland, Saarbrücken. DBpedia, I think, is from Berlin or Potsdam. Yeah, they have the biggest knowledge bases. So they are interlinked with each other. So when you want to know further things, then you find in one knowledge base, you go to the same as, and then you go to the other data source, to the other knowledge base. Use cases. Why do we need knowledge bases? As you might already know, that Watson from IBM won Jeopardy. Jeopardy is a quiz show where people are and they have questions. In Jeopardy, you see the answer. So, for example, you see the answer. She is a famous actor, played in the movie blah blah blah, and born in blah blah blah. And then the person says, "Who is Julia Roberts?" That's correct. That's the quiz show idea. And IBM developed an artificial intelligence robot. An artificial intelligence application is the use case for those knowledge bases. And they used Yago and DBpedia to query what the answer of the quiz show question is. I don't know if I find the video. Oops. Watson Jeopardy. Watson and Jeopardy challenge. And Watson won the Jeopardy challenge. So here you see there are two humans playing. These are the categories of the prizes. And here's the Watson computer. Here you already see that Watson gave the correct answer. And it is very funny because sometimes Watson says absolutely stupid things, so which doesn't make any sense, and this makes it very funny. But Watson is not only made for Jeopardy, It's a very big project by IBM, and it's a lot used for clinical research. So Watson can analyze the symptoms of a patient in a clinic, and then make suggestions which medicine should they give, and which illness is there, and so on. So for clinical research, Watson is used, but it can be used for answering anything. So natural language question answering, it's called. I give a question in a natural language. For example, how old is Paul McCartney? You can ask your Amazon or Siri or Google bot those questions, and maybe, as these are commercial products, they have their own knowledge bases, but maybe these knowledge bases, yeah, they are not open, but maybe they used input from Yago and so on. I don't know, but you can ask, of course, these bots questions, and the answer for those questions can be found on Wikipedia, for example. And first of all, you extract the data from Wikipedia, then you have facts, for example, in RDF format, and then such a bot can reformulate such a natural language query, like how old is Paul McCartney, into a SPARQL query. That's a query language on RDF data. So you find here, okay, Paul McCartney is a name. How old means, okay, I come closer to my answer when I find out the birth year of Paul McCartney or the birth date. So your system has to understand this query, transform it into a SPARQL query, and then have all the data that is necessary to answer this query. Okay. You can also use these knowledge bases to improve the web search. So here's a screenshot of Google. When you write something into the Google input, then it automatically shows a result before you submit the query. So in the first iterations of Google, you wrote your question there, birthday of Paul McCartney. Then you find a list of links. Then you click on the first link. In this page, you see the answer. Then they added the answer directly on top of the page. So when you Google for birthday Paul McCartney, then you see here the most important information directly here. Maybe they extract this at this moment from Yago, or they have their own knowledge base, which is, I think this is the case. And you also see the result directly here in the search input field, or $5 to euro. You immediately see the result here. But okay, this is just a calculation, not querying a database. But birthday of a person, therefore you query a database. Now we come to the language SPARQL. SPARQL is a recursive acronym standing for SPARQL Protocol and RDF Query Language. So basically it's the query language on RDF data. So you have a large set of RDF data, and you now want to ask the question, in which year was the game Risk published? Or in which year was Paul McCartney born? Let's try this here out. The main challenge is you need to know how the resources of the subject and predicates and objects maybe are called. So you see here the query. So this is the prefix declaration. It does not really belong to the query, but without this prefix declaration, it would not be a valid query, because then it says, hey, what is Jago colon? I don't know what this stands for. Therefore, we have this prefix declaration. Jago stands for this one. It also works without any prefix declarations, but then SPARQL looks very ugly. Then you need to write the full URL here and so your query would look like this. You would have resource URLs as a subject, as a predicate and object. And that's the idea of SPARQL. In the where clause, so basically it looks kind of SQL, right? Select something, no from. There's also from in SPARQL, but this is not important for us because the from is where we are connected to. So I am now connected to Jago and I ask Jago questions. Select the year. This is a variable that I introduced. So question marks are variable that I introduce. I can also call it y. Yeah, so basically this is a placeholder, a variable. Where, and then dot separated a list of facts. And facts are RDF triplets: subject, predicate, object. For the subject, you use either a variable or a resource. For the predicate, you use either a variable or a resource. And for the object, you use either a variable, a resource, or a literal value. When you use a variable, then this is open. So Jago was published in X. Now the database looks at the RDF data, finds, so this is like matching, finds a triplet that matches this triplet here. Risk game, date published, and then anything. Haha, I found it. I found risk game, date published, 1957. So X is 1957, and then I can return X. So it's like Neo4j. We have these patterns of a graph. Within the graph, we introduce variables X and Y and P and what else, and then we say return X. And here it's the same. Select X, where, and then a list of triplets. Let's try this out. I called it year, not X, to make it better understandable. But basically you can call these variables as you want. Good. jago-knowledge.org/SPARQL is a SPARQL interface. Oh, here's my previous query. I wanted to try out if SPARQL also has aggregation functions like count, and yes, it has. Count star as question mark X. I come to this query later. It takes some time because the database is big, the machine is slow, and many people are working in parallel here. But you can download Jago instead. If you plan to launch several queries, please download Jago. Jago download. Jago 4 is the newest version. So Jago is not a software product. Jago is a database, a collection of data. And here's the full file. 2020, newest version. labels. Megabytes, gigabytes, 27 terabytes when I see it correctly, plus all the other files. Yeah, it's a big, and it's zipped, so it's compressed. Okay, error. Let's come to this query here. Okay, 1957. I ask risk, date published in a year, and then I want to know the year. Or I say, give me all games, and then date published in a year, and I want the game, no comma, and the year. Now I should introduce a limit because many results are shown here. So each game together with its year, it's found here. So these are the basic queries. You introduce subject, predicate, object facts in the where clause. Then you leave gaps with variables, and in the select you use these variables for getting the answer of the query. So it's stuck. Yeah, okay. Let's come to more complex and more simple queries. There's a question in the chat. Is the question marks in front of the variable needed, or is it just best practice to do so? Yes, it's needed, because when it's not starting with a question mark, it's a string. So let's make a no, it's not a string. Let's try it out. Clear. But wouldn't it match anything that has a date published attribute, not just games? Yes, exactly. In my example, I have only the triplet whisk game, date published, year. I did not. You mean the where I used a question mark here. So for this risk game, I know that it is a game. But in my previous example where I said question mark game, date published, year, I try to reload. Here it is. So here we had so this is not a game, this is a creative work, this is a book, Les Paul something. So I want to only have games, so I add game RDF type. How was it called? I don't remember, so I call it X and I retrieve X. And I hope that a game is in the result. Here, creative work thing. Yeah, it's schema : game, I think. So I add another triplet to say that this thing that I want to retrieve the year from is actually a game, so type game. Now I have only games. Delta Green was developed published in 1997, and I click on it, tabletop role-playing game. And clicking on something is good for exploration. So when you don't know, is it called schema::game, or is it RDF::game, or is it called date published or date published with a small p and so on, simply click on something or use the Yago search, browse here and search for Paul McCartney. And click on it to see all the data, and this helps you writing queries. It is called schema::given name and then Paul given name. So give me all people who are called Paul. Select, I come to this later. So there's a person, schema given name, is it written like this? Yes. And then Paul given name. Okay. And now I output the name of the resource. Maybe this is because of the special characters here. How did I fix the special characters? With a backslash escaping. Oh no, here. Okay, 50, because I used limit 50 here. 50 people called Paul. Bono is called Paul. Yeah, Paul, Almond, Paul, and so on. Yeah, so now I output the name of the resource. But if I want to know, let's say, the last name, then family name. So then I introduce another triplet, and P has the family name F. Let's output both. And now I have the name of the resource and then the family name. And the family name is not a string. You see this on the Yago colon here. Family name is also a resource. Resource of type family name. Yeah. Type surname it is called. Type Yago surname. Okay. This describes the full graph, and what I wanted to try out is whether the question mark is necessary. Yes, it is. Question marks are necessary for the variables. Okay, finding everything. There's a question for that game year query. Won't you need to specify the table of the... Yes, I did this. And I forgot to introduce the short syntax for that. So here I also did not filter that this is actually a person. So this finds everything that has the given name Paul. It can also be a dog or something. So it would be recommended to firstly check for the type. And I did this with rdf::type and then schema::person. So it finds the same. And for this rdf::type, as you do this very often, there's a syntactic sugar. P is a person. And P has the given name Paul. And P has the family name F. Give me F. Okay. Subject, predicate, object, simply using variables for everything. There you can explore Yago. So simply put this here and you find 50 facts. These are the first 50 rows of the Yago file if you would download the whole knowledge base on your machine. Undefined has a start date, the 4th of April, whatever this is. Yeah, but typically you use something that is fixed here. Find cities. This is a query similar to the one finding a game, finding all games, or finding all people. So all cities, I still use subject predicate object, and subject has the type city. And for this colon RDF colon type, you can also use the And the magic in SPARQL is reusing the same variables in different predicates. So this is the same variable here and here. And with these facts, with these triplets and using the same variables, you can also make graph queries. First, a question for you. Select star. Select star is also possible. Question mark P is a person and C is a city. So P is a person and C is a city. What do you think? Is this an erroneous query? Is this incorrect? Is this not a valid query? Does this join people and cities? Is this a union or is this a cross product? I didn't tell you the answer, but think a bit. What do you think? What makes most sense? Go to frage.de, Frage with 2a, and answer the question, does this query here not compile? Does it perform a join, a union, or a cross product? We have 33 or 34 watchers currently. So please, 25 people, answer this question, then I show you the solution. If you have no idea, then think of SQL. Okay, 7 more answers, please. Five. Who hasn't yet answered? Go to frage.de, open it in a new tab on your browser or open it on your mobile phone. What do you think? I want to know, what do you think is the result of this query? It is a cross product. It was not so easy, but this is the most given answer. This is something I like. In SQL, take a look at this query. select star from people P, comma, cities C. This is a cross product. Every person with every city. This is a cross product. Every person with every city. Why is it a cross product? Yeah, because that's the definition of the from clause. When you have two tables in the from clause, it's a cross product between these two tables. Every person together with every city. When you have 1,000 persons and 100 cities, and the result has 100,000 rows. Peter Berlin, Peter Hamburg, Peter London, Peter New York, every person with every city. And typically you continue here, and in the where clause or in the join on clause you have a where predicate. P dot born in city equals C dot city ID or something, to not find every person with every city, but every person with their city. And here we also have not interconnected our variables P and C. So an arbitrary person and an arbitrary city. So this is a cross product. But now we want to connect the things. We want graph queries. Before we do that, I show you some more details of the things that we already did. We separated with a dot multiple triplets. So when you have only one triplet, you don't need a dot. So the dot is not necessary at the last triplet. But the dot separates multiple facts. So we did this here. Subject, predicate, object, and the subject is a place or something. City. This is invalid. Hey, why is here a question mark? Now it is valid or well formed. Okay, now we find everything about cities. This is the meaning of a dot. And then there is another separator, semicolon. After the semicolon, you omit the subject because it just means the subject is the same as above. So here you can also write semicolon and then not game. So this is a bit less to type. Game is of the type board game and has the schema Hasbro. So this is the meaning of the semicolon. And it is exactly the same that I had before here with a dot and then game. So they share the same subject. So this is just syntactic sugar. First names and last names of people born on the same day as Paul McCartney. So now it gets interesting. We need multiple facts. Paul McCartney is our resource that is given. Let's start with this node in the graph. So Paul McCartney has the birth date, my variable called birthday. Don't know what it is, but let's say it's the 5th of May, 1996. No, it's not true, but this is a date, and we search for other people that also have this birth date. So P also have the birth date, what we found out here, and P has the type person, to not find dogs and cats, which have the birth date same one as Paul McCartney, because only people born on the same day. Then the given name I want to store in the variable first name, and the family name I want to store in the variable last name. First name and last name I use in my select clause because these are the two columns that my result should have. And order by is similar to SQL. I can order by a column descending or ascending, order by multiple variables to order my result set. Let's execute this. So when I just copy paste it here, it says, oh, prefix Jago is not defined. So I need to keep these prefix declarations. Play. So we find people born on the same day as Paul McCartney. Heinz Ehrlich, Jill Gibson, and so on. So I don't return the resource, but their first name and last name. I can also return the resource, select P in the first name and the last name. Then I can click on, hey, Heinz Mehrlich, Heinz Ehrlich. So Heinz Mehrlich is a German politician and has a given name Heinz and the family name Ehrlich. But why Mehrlich? Let's go to this Wikipedia page. It's a German Wikipedia page. So I think this is an error. So they extracted the surname incorrect. Family name Ehrlich. Okay. Errors are there, of course. And this is now using different resources. This is the resource Paul McCartney, and we traverse through the graph to other resources, to other people who are born on the same day. Oh, I already gave the solution for this task here, but please do this. Use the semicolon notation for this first query here. The game is a board game and the game has publisher Hasbro. Yeah, there's an alternate name, Mehrlich too. Maybe they mismatched info. Yeah, but on the Wikipedia article, yeah, they put this information in the alternate name property. Yeah. But it should not be an alternate name, it should be the real name, right? Don't know. I don't know Heinz Mehrlich or Ehrlich. So this query above, select game, where game Rdf type. So use the semicolon notation for that. Be very quick. I give you the solution in 30 seconds. $20. 10. 2, 1, and 8 seconds because of the streaming delay. I need to think as well. Board game, schema, publisher, Hasbro. Here's a dot. Here's a game again. Here's also a game again. So green is absolutely correct. Game is a board game, and then after the semicolon you just write predicate object and not subject predicate object. Yeah. Up to now we only used resources. Resources for the subject, resources for the predicates, and resources for the object. Okay, for the object. Yeah, here we use the resource for the object, schema colon person. But many data in RDF is also literal values, strings, integer, and so on. And there we can use a filter clause in the where clause. So after we specified our pattern, so basically this pattern here is like the match clause in Neo4j, right? And then the filter clause is the where clause in Neo4j. So we, up to now, we say, give me a person that is type of person, and this person should have the birth date, any birth date, write it into the variable birthday. And now we further filter that not an arbitrary date should be within this variable, but that the birthday should be larger than this and smaller than that. So basically all people born in the 1960s is this query about. Let's try it out. Again, I use my prefixes. Even if I don't use the RDFS and RDF prefix now, I use RDF, but not RDFS, and in this case, not the Yago prefix. But I simply use it because then I don't need to remove them and so on. Here I don't have a limit clause, so this finds a lot. Now it finds only 50 people. So many people born on the 1st of January 1960. And so this is a very, very big knowledge base here. I can say order by birthday. I think I have to write descending. SPARQL order by descending. Desk and then in brackets. There comes a link in the chat. What's this link about? Is it about Heinz Mehrlich? Wikidata. Wikidata, the other knowledge base. But their family name, yeah, it has the same information here. Okay. Maybe this knowledge base, Wikidata and Yago, extracted it from the same data source and the data source was wrong. Or some automatic typo corrections happen because more people are called Ehrlich than Mehrlich. I don't know what the reason is. And maybe there was an article in the web about this person where somebody wrote a different name and then Yago and DBP Wikidata extracted from this article erroneous information. Don't know. Okay, now I query the this is not from the 1960s. All people living in the year born in the year 1960 birthday, so this would be in the 1960s. So in this much more people. So this filter clause is used for filtering on the string or integer or date or other values. So filtering not on the resources but on the property values. Before I want to finish with SPARQL, so basically this is everything you need. You list triplets. In the triplets you either use a resource or a variable, and then in the select and the order by you use these variables to get your result, order the result, and so on. Group by, just to tell you that SPARQL is very powerful and that its development is still ongoing, and it is getting more and more features. There's also the group by feature, and I just want to show you that it's very similar to use than in SQL. So in SQL you specify a group by clause listing one or many columns. These columns you are allowed to use in the select clause. So when I group by birthplace, I have as many groups as there are distinct values in the birthplace column. So here birthplace is a variable. Let's say each person has a birthplace and there are 100 different ones. Then we have 100 groups. I can return this birthplate. So I have a Berlin group, a Regensburg group, a London group, a New York group, a Niederstadtfeld group, a Straubing group, a Munich group, and many more. So as many as we have different values in this for this birthplace value, and then all people, all rows that would originally be returned without the group by are now collected within those groups. So I have now the Berlin group with all people that have the birthplace Berlin, and I can now ask aggregation function on those entries in a group. So for example, count star. Count star, give me just the number of people in each city. Order by this number. So this shows me that most people who are in the Yago knowledge base are born in Tokyo. Let's use this query and find out more interesting facts about the world. World stored in Tokyo. Let's say P is a person, and I don't group by anything. Just a count star query. Wow. So Yago stores the information about 3.7 million people. Probably not for me and not for you, maybe only very prominent people. Then we can ask what's the most common first name. P has the schema given name first name. Then I say first name count star, no comma, group by first name, order by this construct here, which calculates my count star. Oh, no as. The as num people is necessary to describe the heading of this column here. And I want descending. This takes a long time. descending. Let's introduce limit. Top 5 is sufficient. Otherwise the result is so big. Maybe it takes so long because transferring the big result back to my client. So I only want to have the 5 most common names. So John is the most popular name in the Yago database. Yeah. And there's a question in the chat. Could you also use order by num people? Yes. Here you see on the slides, order by, there we use a variable that I introduced here. So here I wrote order by count star, but I called the count star result num people. So this also works. In SQL, there are strict rules where you are allowed to use your own aliases, but here aliases are everywhere. Yeah, that's the result. Okay, this is SPARQL. One more. Because of the graph traversal. I want to, we already had a graph traversal query. Give me the people who were born on the same day as Paul McCartney. I start at the Paul McCartney node, go to the value where he was born, when he was born, the birth date, and then from this date, which is actually not a real node in the graph, it's just a literal value, but let's say it would be a node, then go to the people who also have this value. So we traverse through the graph. And I make some more examples of graph traversals in SPARQL now, but I'm sure that you would be able to do them by your own as well, with the knowledge that we already had. In which cities were people born that acted in the same movie as Michael J. Fox? The idea is the same in Gremlin, in Neo4j, in SPARQL. I start at the node where something is given. Haha, there's a person called Michael J. Fox. I go to all movies where Michael J. Fox acted in. In the Back to the Future 1 movie, Back to the Future 2 movie, Back to the Future 3 movie, and some more movies. And from these movie nodes, I go to the other actors. Okay, actually I find in the result Michael J. Fox as well, but yeah, Michael J. Fox acted in a movie with Michael J. Fox. Yeah, it's not a lie. And then I go to the cities where these people are born. So my variable movie that I introduced has an outgoing edge to actor. If we talk in edges, when the edge goes from left to right in our subject predicate object. So movie has an actor, Michael J. Fox. So Michael J. Fox has an incoming edge from a movie. So I start here, Michael J. Fox, go to the movie where he played in. These are many movies. Then I go to the actors and then to the birthplace of those. And I return the birthplace and select distinct as like in SQL. It gives you each birthplace only once. When you want to write such a complex graph traversal query, you can do this step by step. So let's do it step by step. Let's start with select movie, where movie has the actor Michael J. Fox. Give me all movies in which Michael J. Fox was an actor. Back to the Future, Stuart Little 2, The Michael J. Fox Show, and so on. You find all movies. Now, from those movies, you go one step further. Who are the other actors? So, I can use semicolon notation here. For this movie, I want to find actors A. And let's return the movie name and A. So this is now a big result. 1,300 entries. So in the Back to the Futures movie, there's also Billy Zane and also Lea Thompson and also Michael J. Fox himself and also blah blah blah. And then in Stuart Little 2, there's also this person and so on. So this is now a big result. And where are these people born? Dot. I'm finished with facts about that movie. A. How is it called? Birthplace with a capital P. If you don't know how is it called, then simply click on such an actor. Here, Lea Thompson. Birthplace, Rochester, Minnesota. Okay. So A is schema birthplace. P like place or birthplace, and then I return also birthplace. Now I return more than I want. So Michael J. Fox acted in the movie The Good Wife. John Pankow also acted in that movie, and John Pankow is born in St. Louis. And these are all the facts. So these are less facts than before, than in our query before. And the reason for this is, yeah, what do you think? Write it in the chat. Why do I have 1,300 facts about movies and people who acted in those movies as well? 1,301. And now I simply want to add another column. A has a birthplace. Birthplace. Why is this reducing the number of results? Write it in the chat. So typically would say you're also 1,301. The same movie, the same actor, and then the birthplace of this actor. Why is this number now smaller? Why is it smaller? It should be the same number. It should not be bigger than 1,301. This would mean that there would be people born in multiple cities. Makes no sense. Not every actor has a birthplace. Exactly. Of course, every actor has a birthplace, but some actors have a missing birthplace. So it is not present in the Yago knowledge base. For some actors, we don't have the information where are they born. When I search on Wikipedia for a person, Jim Gray, a computer scientist, born in San Francisco. For this person, we have the information, but for other people, maybe this fact is missing and Jago does not know that. So there is no triplet. Where are we? Here. There is no triplet. Let's say Peter Peterson. There is no triplet Peter Peterson birthplace something, because it is not stored where Peter Peterson is born. So this triplet is simply not found. So it does not match to that data, and this means it is not returned anymore. It is like a join that finds no join partner. Yeah. There are clauses like I don't know it, optional. There's the optional clause. How does it work? SPARQL optional. There you can say here optional something. Let's try it out. This again finds 1301 entries, and now you see here are null values now. Okay, for Margaret Colin there is no birthplace, so it still matches this expression here, but as we specified this as being optional, if it does not match it, we simply fill it up with a null value. So basically this is like an outer join, like a left join. I want this actor even if it does not find a join partner in the birthplace. So here Melissa Benoist, when I go to that page, birth date is there, but no birthplace. Yeah. Yeah, so Jago does not have the information where she was born. Okay, that's the idea of RDF, the semantic web, and the language SPARQL. Do you have any questions? Exactly. In the other chat, there was the try of the explanation. The birthplace is unknown and null equals something is always false, like in SQL. This is not the reason in SPARQL. Oops. In SPARQL, SPARQL is like pattern matching. We find in the graph this pattern here, and this pattern is simply not found. We find not the pattern. How was she called? Melissa Benoist, birthplace, and then a placeholder. This is not found in the graph, so it is not returned here. So, do you have more questions? General question, dates for the exam have been released? Yes. Date for the exam is released, and it will be a written exam. Can we query things that don't have some properties? Find all actors that don't have a birthplace. Yes, this is possible, but I don't know the syntax. So this would be like is null or is not present the absence of a property. Yes, but I don't know how to do this. But yes, it is possible. Is there any information of the type of exam? It will be written. If you are a student from a very different university and you are not in German, so you are a student of a Hong Kong university or so, then you can do a remote exam. But for all people who have a matriculation number and are students of a study in Regensburg at the OTH, who are students for the master, you have a written exam in Regensburg. Link is missing between actor and birthplace. Exactly, that was the reason why we did not find 200 facts which were found in our first query when adding the birthplace. Do you mind adding few more questions during the lecture? It really helps following the lecture. Is recurring. Yes. Today there were only 2 frage.de question and 1 additional question where I asked something in the that you should write the answer in the chat. Yes, I try to do this as often as possible. Will there be an exercise sheet on SPARQL? Yes, it will be published this evening. And next week on Friday we will discuss that. Not this week Friday because there's a holiday, but there will be an exercise about SPARQL. But as we start with a new topic next week, no, this week there will not be an exercise sheet, sorry. I will make a bigger exercise sheet next week with 2 exercises, 1 SPARQL exercise and 1 SQL exercise, because we will continue with SQL next week. This will be a very interesting lecture, because we do recursive SQL queries, because we learned so many new languages and graph databases, and then let's go back to SQL. How could we do things like find how many people acted in the movie Back to the Future? Okay, this is a count star query, but more complex queries which needed closure computation, recursive queries. We do this next week, and then we have an exercise on SPARQL, just basic queries, just what we did here, and then an exercise on recursive SQL. Could you upload the first part this week? Yes. Okay, good idea. I will upload. Could you upload the first part of the exercise sheet this week so we can start doing the part over the weekend? Okay, I will upload the first half of the exercise sheet, and then I write exercise 1 SPARQL, and then to be continued on the exercise sheet. And next week you will see the full sheet, and we will discuss the full sheet then on Friday in a week. So this Friday no exercise. See you on the lecture next week, Tuesday, about SQL, graphs in SQL and recursive SQL queries. See you then. Goodbye and thanks.